Well, this lecture gives a brief introduction to Bayesian ordinary least square or Bayesian estimation of multiple regression. Before I get into the technical details, I'd like to help you brush up your memory about this Bayesian paradigm, especially the workhorse of Bayesian estimation. So our goal in Bayesian estimation is to derive this posterior distribution of the parameters, right? So P of theta given D here, right? And D corresponds to theta, and theta is the parameter of our interest. And based on the Bayes rule or Bayes theorem, and the posterior probability distribution is proportional to, first is likelihood, right? The probability of, or shall I say the likelihood of the data given the parameters multiplied by the posterior, that is the probability density function of theta. Theta. And for Bayesian multiple regression or Bayesian linear regression, usually the likelihood function is assumed to follow normal distribution. So here we see y turns out to be a conditional y, right? Conditioning on x and beta, right? Equivalently, every term, follows a normal distribution, right? Follows a normal distribution. And then we need to supply this prior probability density for the parameters. Then we can execute Bayesian estimation, either turn to the conjugate priors to have closed form solution and then simulate from that posterior, or we can turn to, in most cases, turned out to be, a majority of the cases turn to MCMC, that is Markov chain Monte Carlo simulation methods, which has become the dominant method of Bayesian estimation. Before I get into Bayesian multiple regression or Bayesian linear regression, I'd like to brush up your memory about normal distribution, since the priors and likelihood both use normal distribution. Okay? So what is a normal distribution? Well, let's begin with standard normal. When we say standard normal, basically we say, well, this random variable follows a normal distribution with a mean of 0 and standard deviation, as well as variance set to 1. So the probability density function of a random variable that follows a standard normal distribution has this form, right? 1 over square root of 2 pi multiply the exponential function of negative that random variable squared divided by 2. Okay? And its cumulative density function follows this form. Basically, it is integral of probability density function. Okay? So what is normal distribution? Well, normal distribution or normal distributions do not have such special parameters. Let's say mean is 0 and standard deviation is 1. So for a kind of commonly used normal distribution, okay, commonly seen normal distribution, we have a mean of mu, right, and standard deviation to be sigma. And its probability density function, the probability density function follows this form. Okay, that is 1 over sigma multiplied by square root of 2 pi, the whole term multiplied by the exponential function of the term within the parentheses. Okay, and mu, again, mu is population mean, okay? The parameter for mean, okay? And sigma is the parameter for standard deviation. And the cumulative density function, again, takes this integral of probability density function.